tutorial, we will be calculating entropy. These are molar entropy values of substances in standard states, meaning at 298 degrees. Standard entropies tend to increase with an increasing molar mass. So if we look at these, as those molar masses increase, the entropies increase. However, that's not necessarily 100% true 100% of the time, because of the fact that it also depends on the complexity of the compound. Larger and more complex molecules have greater entropies as well. Entropy changes for a reaction can be estimated in a manner analogous to those of the delta H is estimated, which we've done in the past. Look at this little zero on top. A lot of times you'll hear that referred to as S naught or H naught. Is referring to this entropy at standard state. So essentially we're taking the sum of the entropies of the products times their respective coefficients in a balanced chemical equation, minus the sum of the entropies of the reactants at standard state times their respective coefficients in a balanced equation. Let's do an example of this. We have 4NH3 as a gas. Notice they actually have to stay the physical state there, otherwise you could get the wrong entropy. The state of a gas will not be the same as that of a solid. Remember, entropy increases as it gets warmer. Oxygen plus 5 oxygen in a gas state yields 4NO at a gas state plus 6 H2O in a gas phase. So first thing we're going to do, the products minus reactants, so it's always going to be the right side minus the left side. We can sum up the right side. So we have 4 times NO, which is right here, 210.8, plus 6 H2O, we're going to multiply that out and add it together, and that comes out to be 1976 joules per Kelvin. Because of the moles out here with the coefficients, the unit of moles here cancels out, so we only have joules per Kelvin when we're done. Now we're going to subtract that from the reactant, so we have to calculate that. We have 4 NH3s, which is 192.8, plus 5 O2s, which is 205.2. Multiply and add those together, and it comes out to be 1797.2 joules per Kelvin. Subtract that out. 1976 minus 1797 comes out to be 179 joules per Kelvin. Let's do another one. So it's the products minus the reactants. So 2H2O, which is 188.8, plus 2SO2, which is 248.2. Multiply that out and add it together, and that comes out to be 874. Now we have 2H2S, which is 205.8, and 3O2, which is 205.2. Multiply that out and add them together, and it comes out to be 1027.2. The products minus reactants, so 874 minus 1027.2, it comes out to be negative 153 joules per Kelvin. Because of the fact that that's negative, that automatically means that this is a non-spontaneous reaction at standard state. Okay, so entropy changes in the surroundings, because we're looking at the entropy of the universe, of both of those surroundings and system added together. So we know how to calculate the system by the chemical reaction. Let's start talking about calculating the surroundings. Heat that flows into or out of the system changes the entropy in the surroundings. For an isothermal process, which means at the same temperature, the temperature does not change, the delta S of the surroundings is negative heat of the system divided by T, temperature in kelvins. Make sure that's in kelvins. At constant pressure, the heat of the system is simply the delta H of a standard state for the system. The universe is composed of the system and the surroundings. Therefore, the delta S, the entropy change of the universe, is equal to the system and the surroundings added together. For a spontaneous process, the delta S of the universe has to be greater than 0. It has to be positive. So let's calculate the entropy change in the surroundings this time, associated with the reaction occurring at 25 degrees Celsius. 25 degrees Celsius, you have to convert that to kelvins before you do anything else. So 25 plus 273 comes out to be 298. So calculate the entropy of the surroundings. That's going to be the heat, the negative heat, you're going to have a double negative here, which means it'll come out positive, divided by 298. That's going to come out to be positive 2.86 kilojoules per Kelvin. At this point, I want to point something out. When you're given a delta H, that's typically going to be given in kilojoules. When you're given an entropy, that's typically given in joules. In order to add those two together, you need to convert one or the other. Typically, people convert the enthalpy by multiplying it by 1,000 before you have to add it together, because you need to make sure that those prefixes match up. Alright, so part B, determine the sign of the entropy of the system. So it's not asking us for the whole number. It's just asking us for the sign, if it's going to be positive or negative. We can look at that by just looking at the chemical compounds. We have 1 C3H8, 5 O2s. That's a total of 6 moles. We have 3 CO2s and 4 H2Os. That's 7. It's becoming, there's more moles on the right, meaning that it's going to be more disorganized. So that's going to be positive. Determine the sign of the entropy change for the universe and whether it will be spontaneous. So we know that the delta H of the surroundings is a positive. We know that a delta H of the system is a positive. So delta S of the universe is positive plus positive, meaning that the delta S, the entropy change for the entire universe, is going to be positive, which means it will be spontaneous. Okay, we'll do one more, just like that. We have the reaction 2O2 plus N2 yields 2NO2. If we know that the delta H of the reaction is positive 66.4 at 25 degrees Celsius, determine the delta S of the surroundings. So delta S, the entropy of the surroundings, is equal to negative the delta H, 66.4, over the temperature in kelvins, 25 degrees, which would be 298 Kelvin. Divide that out, and it comes out to be negative 223 joules. It actually comes out to be 0.223 kilojoules per Kelvin. I went ahead and multiplied it by 1,000 to get it into joules, so that way I can comparing the entropy of the surroundings and the entropy to the systems in the same units. Determine the delta H of the system. Well, we have 2 O2s and 1 N2, so we have 3 on the left. We only have 2 on the right. So the entropy is decreasing because you have fewer moles on the right. So that means that the surroundings is a negative, the system is a negative. Will this process be spontaneous? Well, delta S of the universe is the systems plus the surroundings. So we have a negative adding to another negative. The outcome is going to be negative, meaning that it is not going to be spontaneous. And that's how you calculate entropy.